In today's lesson, we're going to be looking at doing confidence intervals for the means. We'll be first looking at what it's called a t-distribution, and then we'll look at how to use that to create confidence intervals. Now, you're probably going, wait a second. We've already been creating confidence intervals for the mean, right? Here's our model that we had from last time. You have your mean as this, and your standard deviation for your mean is your standard deviation for the population divided by the square root of n. But in real life, you rarely know the n, all right? So what do we use if we don't know, the sigma? Most of the time we don't know it, all right? That's the whole point of taking samples. But we could calculate S. S is basically the standard deviation for the sample. Remember, we were doing that at the beginning of the year. You would put the data in the table, and then it would spit out, we would do like one var stats and would spit out the data. So we could take that S and use that instead of the standard deviation for the sample. And this actually worked well for many years, even though S is technically a statistic, and it varies from samples to sample. Now, they did notice more problems when n was not large. And the person who really pioneered this research, he saw that extra variation messed up p-values and margins of error. So who was this guy? His name's William S. Gosset. He had a dream job, the quality control engineer at Guinness Brewery, pretend that says brewery, in Dublin, Ireland. So he had to basically test the beer, all right? And you're thinking, okay, well, he decided he liked his liver, so he didn't want to use a huge sample size. He would use a small sample size of 3 or 4. But he realized his tests weren't quite right. He was using an alpha level of 0.05, so he figured, okay, my type 1 error is 5%, so I should be rejecting about 5% of the good batches, and I can live with that. So he had the good batches sent back for further testing, and then realized he was rejecting 15% of the good batches, and thought, okay, this doesn't make sense. So he actually went ahead, and being the good quality control engineer he is, he did further investigation, all right? And he actually realized that the distribution of the data was changing for very small samples. And he created a new model called the t-distribution by simulation. What he did is he actually took little slips of paper and did hundreds of samples. This took him a year, used a mechanically cranked calculator, and came out with the exact formula for the t-distribution. This was later confirmed by another mathematician years later, all right? He published this under a different name. It's so-called the student's t-distribution. And the reason he did that is Guinness Brewery thought, oh, trade secrets and stuff like that. So they didn't want a lot of publishing going on. So you won't see Gosset's distribution. You're going to see student's t-distribution. So what did these different distributions look like? Well, they actually, when n was very large, remember we said that it looks very normal. So when we have 40, it's fine. But when we start playing, and let me see if I can get my pointer. Let's see. There we go. So when we start playing with the degrees of freedom, so he actually had to calculate all these different curves. So he went and he did different degrees of freedom. Remember, degrees of freedom is n minus 1. So it's your sample size minus 1. So as you got down to very small samples, you can see we have fatter tails here, right? And the margins of error are going to get bigger because the spread is bigger. The confidence intervals are a bit wider, and the p-values are a bit larger. Now, the student's t-models are still unimodal, symmetric, and kind of bell-shaped, like the normal. And in fact, if you did infinite t, they're exactly normal. So we could have pages and pages of tables in our book with different degrees of freedom. But they said, you know, most of the time we're just looking for certain probabilities, so we'll take the most popular ones and we'll list it for the different degrees of freedom. We'll look up the value for you and put it down. Okay, So usually, and I have a table for you as well, so you can look it up manually. All right, and oh, notice that it's to the right. That's interesting. Okay, so you can do this on your calculator as well. So if you want to get a probability given a t-value, now remember a t-value is a lot like a z-value, except it's for the student's t-distribution. So it's not for a normal. Z is for normal, t is for the t-distribution. So to go ahead and do that, you want to press second distribution. It is a distribution model, right? And you're going to scroll down to 6 TCDF, so T for the t-distribution. And you're going to enter your values in the format of your, kind of like your Z1 and your Z2. I should call that T1 and T2, all right? And then your degrees of freedom. Now you notice I got one value when I did 1.645 to 1,000, and I can do it for a different value, still with different degrees of freedom, 1.645 to 1,000, and now all I'm changing is my sample size to 25, and you can see I actually have a different probability. So your calculator does this, it will spit it out, and those are the steps, and you really should change these to t's. All right, so this returns a probability for getting the t-value with the specified cutoffs and degrees of freedom, okay? So if I want to find t-value from probability, you remember with normal distribution, we would do inverse of the normal distribution. Well, guess what? We have an inverse of the t-distribution. It's number 4. And you're going to enter values for the probability, which is all you had to enter before. But now, because we have different models with different distributions, degrees of freedom, we have to enter the degrees of freedom. And you notice the calculator actually sits and thinks for a little bit on these. So there's, because of all the different models. So we'll do this with another number of degrees of freedom here. And there it thinks, and it spits it out. So this returns a t-value at which the probability to the left is the entered value and the specified degrees of freedom. Okay, so how about if we're going to do a model, let's talk about our assumptions and conditions. Independence is still very important. The data comes from a random sample or suitably randomized. SRS are ideal. Now, some of you always want to write SRS. It's only a simple random sample if they tell you they did a simple random sample, okay? The 10% condition still applies if the data are sampled without replacement. The sample should not exceed 10% of the population. Now, you notice I don't have the success failure condition on this. We were doing sample sizes of 3 and 4. How am I going to exceed 10 if I don't even try 10 times? So that one doesn't really apply to this. Now, we do need a nearly normal condition for our original data. So the best we can do, all we have is our sample. So if our sample is less than 15 or so, we're hoping it looks kind of normal. You know, like there's a peak and it's nicely distributed. For n at greater than 40 or so, you can use this model even if the data are skewed, okay? Now, in between, all you need to know is that the data is unimodal, one peak, and symmetric, so you can fold it in half and it looks about the same. You should always make a histogram for all of these, even for n greater than 40. So that leads us to our model for our sampling distribution of the mean. So, provided that the independence assumptions and the nearly normal condition is met, we can model our sample with same mean, and our critical value, which is a t-value, is going to be the mean minus, the sample mean minus the whatever we use, right? And your standard error for y hat. And remember, we calculate our standard error by dividing our sample statistic by square root of n.